Hello, my name is Francesco Luzi, and I will be presenting Transformers for Recognition in Overhead Imagery, a reality check. Transform-based models have emerged superior over their convolutional counterparts in many computer vision applications. We aim to determine if this was the case in segmentation of overhead imagery as well. The figure on the right is an example of the application we are investigating. More importantly, we sought out to rigorously isolate and test the effect that including transformers had on performance over only convolutional-based models. There are several state-of-the-art models used in segmentation of overhead imagery. We choose to focus on UNet, shown on the right, for a number of reasons. It is highly used and well-performing state-of-the-art model due to its encoder-decoder architecture, with skip connections that retains accurate spatial fidelity in its output. It has easily available code and benchmarks for itself and its many variants, and there are well-performing hybrid and fully transform-based variations of the UNet. The three variations we evaluated were the standard UNet with convolutional encoder and decoder, shown on the left, a trans UNet shown in the middle with a convolutional encoder, followed by several transform blocks and then a convolutional decoder. Lastly, we looked at swing UNet, shown on the right, which is a variation of the UNet in which each convolutional block is replaced by a swing transform block. All models were trained and tested on a composition of two datasets, Inria aerial competition dataset and the DeepGlobe competition dataset. Together they form a large and diverse dataset spanning 9 cities, 5 countries, and roughly 800 kilometers squared, taken at 0.3 pixels or meters per pixel resolution. A very important part of our work is that we ensure the models are trained fairly. To remove as much bias as possible, we use Bayesian Optimization to search the hyperparameter space for each model. We allow each model sufficient time to converge to a good set of training hyperparameters such that the space is adequately searched and the performance no longer improves with further searches. Below, we show each model's search space for 2 hyperparameters. We found that TransUNet outperforms all other models across almost every city, shown in bold below, and that SwingUNet had the worst performance by far. We also see that while TransUNet outperforms UNet, the difference isn't very large and cannot be attributed to transformer alone, with only this information. We then proceed to determine the effect that the number of transformer layers has on TransUNet's performance. We found that the optimal number of layers, 8, was lower than the standard count of 12. We also found, interesting enough, that the TransUNet with 0 transformer layers and 1/5 the number of parameters performs roughly as well as the UNet. This implies that some of the performance gains that TransUNet has over the UNet may be attributed to factors other than the transformer layer. To isolate the improvement to performance attributed by transformer layers, we substitute the transformer portion of TransUNet with fully connected layers shown in line 1 of the table and convolutional layers shown in line 2. We found that while transformers provided the best performance, the improvement over simple convolutional layers was very minor. In conclusion, we determined that while transformers can sometimes provide improvements in performance, these improvements may depend on the application and may be more minor than they appear. Thank you.